Good afternoon, everyone. So in the last class, we were going over section 5.3 and section 5.4. So we are talking about the sampling distribution. So the sampling distribution is the distribution of statistics. For example, if we find the distribution for sample mean, or if we find the distribution for sample median, sample variance, and all are statistics. So the distribution of any statistics is called the sampling distribution. So we were talking about the sampling distribution for mean. So if X bar is our mean, then the sampling distribution for mean will be, if you already know that, if n is large, when n become large, the sample size become large, the distribution become close to normal. So here you can see that the first distribution is when n is equal 1. So you can see that the all the densities for all the values of x, the densities are same. They have similar density for all values of x. So this is kind of uniform. But when n increases, when n is equals to 2, this is symmetric distribution, but it has thicker tail. So it's not normal, but it is symmetric distribution. But if you look at this distribution, the variability reduces when n become large. And look at this one, when n is equals to 10, it's symmetric, bell-shaped, and it has also thin tail. So it's kind of close to normal. So if you consider larger n, then it will become more normal. So now we'll talk about the standard distribution for the sample mean. So if x bar is the sample mean, then and n is large. So from the large number property of the large number, we can say that when n become large, x become close to normal. So n will be normal distribution with mean mu. And what is the variance here? Variance is sigma square over n. So why sigma square over n? Okay, so for example, we have x1, x2 up to xn observations, and all are independent and IID distribution. IID means independent and identical. So x1, x2, xn are independent and identical. Are independent and identical. Identical. Okay, identical. That's mean xi's are IID. So why we need independent and identical for sampling distribution? So if x bar is our sample mean, then x bar will be 1 over summation of I is equal 1 to n summation of xi. So this is the definition of the sample mean. So now we need to find the distribution for x bar. We know that when n is large, x bar is normal distribution. So this is called the central limit theorem. So this is the property of large number or large sample. So now we know that x bar, not x tilde, this is x bar. X bar is the sample mean, is normal distribution. But we do not know the mean of this distribution and the variance of this distribution. So how can we calculate the mean and variance of this distribution? So the population mean for xi, for example, if we have the expected value of xi is mu. So why mu? For I equals to 1 to n, because we know that the population mean is denoted by mu. So we are considering the expected value of xi is mu for I equals to 1 to n. So for each one, the mean is mu because they are identical distribution. And we are also considering the variance of xi is equals to sigma square for I equals to 1 to n. So now we know that x bar follows normal distribution for large n, but we do not know the mean for this distribution and the variance for that distribution. What we know that x bar is normal and x bar is equals 1 over summation of xi. So now we need to find the mean, that's mean population mean for x bar. So how can we find the population mean? We can calculate the expected value of x bar. So the expected value of x bar is equal expected value of 1 over n summation of xi, and I is equal 1 to n. Since 1 over n is a constant, we can write this constant outside the expected value. And this is the property of the expected value. You already know that expected value of ax is equal, a times expected value of x. So you already know this property of the expected value. So you already know this property of the expected value. Expected value of x is equals to a times expected value of x. So since 1 over n is a constant, so we can write this one outside, then it will be expected value of summation of xi. Okay, so and the expected value has also nice property. It has distributive property over addition. So that's mean we can distribute expected value to each one. So that's mean we can write 1 over n summation of expected value of xi. Okay, so this is equal 1 over n summation of, what is the expected value of xi? This is mu here, right? The expected value of xi is mu. So we can just write mu, I equals to 1 to n. Is it clear? Do you have any question? Okay. So the next one is, now we have expected value of x bar is equal 1 over n summation of I is equal 1 to n mu. So this is 1 over n. And how many mu we have here? We have I equals to 1 to n. So we have n numbers of mu. For example, if we write summation of 2 I equals to 1 to 3. So that's mean we are adding 2 3 times. For I equals to 1, this is 2. For I equals to 2, this is also 2. For I equals to 2, this is also, I equals to 3, this is also 2. So that's mean we are adding 2 3 times. So we can write this one as 3 times 2. Similarly here, we are adding mu n times. So we can just write n times mu. Now we can cancel out this one and this one, then it will be mu. So that's mean expected value of x bar is mu. So now we know the mean for the x bar. But now we have to calculate the variance of x bar, because to write normal distribution, we need two parameters. One parameter is the population mean, the other one is the population variance. So now we have to calculate the population variance. So how can we calculate the population variance? So variance of x bar is equal variance of 1 over summation of I is equal 1 to n xi. Okay, so now the variance also has very nice property. You already know variance of ax is equal, we can take out a outside. So what will be, so what should we write here? A or a square? Yeah, we have to write actually a square, not a. Thank you. So when you are calculating variance, if you have any constant inside the variance, because variance is the sum of a square. So that means you are taking the a square, then you are taking the sum. So if you take the a square, then a will be also a squared. So that's mean if you take out a outside the variance, then it will be a square. So a square times variance of x. So here then we can write one, we can take out 1 over n outside, then it will be 1 over n square. And we have variance of summation of I is equal 1 to n xi. And variance also has nice property if xi's are independent. If xi's are independent, then we can distribute variance to each one over the sum. So that's mean we can then write 1 over n square summation of I is equal 1 over 1 to n and variance of xi. Because since xi's are independent, otherwise we cannot write this one from here. If they are independent, then we can write this one, otherwise we cannot write. Since we have xi's are independent, so we can use this property. Now we have 1 over n square summation of I equals to 1 to n, and variance of xi is sigma square. We already know that xi has mean mu and variance sigma square. So now we have to simplify this one. So if you simplify this one, then it will be summation of 1 over n square 1 to n sigma square. So how many sigma squares we have here? So we have n number of sigma square and we are adding them together. So if you add them together, then it will be 1 over n square n times sigma square. Now we have n square here and n in the denominator, so we can cancel out 1n, then it will be just 1 over n sigma square, or you can just write sigma square over n. So x bar is normal distribution with mean mu and variance sigma square over n. But the variance of x was sigma square. So that is the difference between the variance of x and variance of x bar. They are not same. Variance of x was sigma square. Now we calculated that variance of x bar is sigma square over n. And you will also see that when you will be solving problem for the sampling distribution. Is it clear how we calculated mean and variance for x bar? Or do you have any question? Okay, so now you can see here how we convert, if x is normal distribution, how we convert x to standard normal distribution. So the formula was, yes. Any question?
Yeah, I was like, what is this stuff for? What is this formula for?
Oh, this formula?
Yeah.
Yeah, I'll discuss this one. Yeah. Okay, so
could you go back to the slide?
X is normal distribution with mean mu and variance sigma square. Then the formula for a standard normal distribution was, do you remember? X minus What is mean here? Mu, right? Divided by a standard deviation. So what is the standard deviation? Is square root of sigma square. So that's mean x minus mu divided by sigma. So if x is normal distribution with mean mu and variance sigma square, then the formula for the standard normal distribution is x minus the mean divided by the standard deviation. Standard deviation is the square root of sigma square. Okay. So now we have x bar is normal distribution with mean mu and variance sigma square over n. So we have to find the standard normal distribution for this one. Then it will be, what is the random variable here? So what is our random variable here? X or x bar? X bar, right? Minus, what is mean here? Okay, I need your response. So what is mean here? Yes, the mean is mu. What is the standard deviation? Yes, thank you. So what is the standard deviation? Anyone? Yes, sigma over a square root of n. You are right. Thank you. So the standard deviation is a square root of the variance, right? If you take the square root, then it will be sigma over a square root of n. So now you can see the difference between these two formula. So when x is normal distribution with mean mu and sigma square, the formula is just x minus mu over sigma. Now we have z is equals to x bar, because the random variable is x bar, minus the mean of the random variable, which is mu, and the standard deviation. Standard deviation is the square root of this number, square root of this one. So which is sigma over a square root of n. So that's why we have this formula for the standard normal distribution for sampling this, for the sampling distribution for x bar. Is it clear now? Now you can see that we will be using this formula when you will be calculating the standard normal distribution for x bar, where x bar is the sample mean, mu is the population mean, sigma is the population standard deviation, and n is the sample size. Okay. And here in this formula, you can also see that this is the standard deviation. So what is going on here? The original standard deviation divided by square root of n. So you are dividing by n. So that's mean if you increase n, this number will decrease, right? So standard deviation is sigma over square root of n. So that's mean if you increase n, this number will decrease. So that's mean the standard deviation will decrease for the sampling distribution. That's mean the variance will decrease. So that's mean the variability will decrease. So when you have large n, the sampling distribution will have less variability. Okay, so now we'll go over an example. What is the probability that a sample of 100 automobile insurance claim files will yield an average claim of this amount or less? If the average, so here this word is very important. So here we are looking for the average claim, not just a single claim. So that's mean we are looking for the probability for x bar, not x. So from this word, we'll come to know that this is the sampling distribution for mean, not just distribution for a single random variable, because we are looking for the probability for average claim. So what is the probability that a sample of 100 automobile insurance claim files will yield an average claim of this amount or less? So that's mean we want to find the probability where x bar is less than equal this number. And we are given the population mean. So that's mean the mu and with standard deviation, that's mean the sigma. So sigma is $600 and mu is 4560. So to find the probability, first you need to convert it to a standard normal distribution. So which formula you will be using here to determine this, you need to know whether you are finding the probability for the mean or whether you are finding the probability for a single random variable. Here you are finding the probability for the mean, so that's why you have to use this formula to find the standardized value of this amount. So the z-square is equal x bar minus mu divided by sigma over square root of n. Now we'll plug in all the number here. X bar, that's means sample mean is this one, 4527.77, minus mu is population mean, 4560, divided by sigma is this one, the population standard deviation, 600, and square root of n, that's mean square root of 100. So if you simplify this one, then it will be negative 0.537. So this is the standardized value. Now you can look at the table or you can use calculator to find the probability. So we are looking for the probability of z less than or equal negative 0.537. So we are looking for this probability. And you can find this probability from the table or from or using calculator, and the probability will be 0.2946. Okay. So we have another example here, the ACT example. Scores on the ACT exam are distributed normally. So it is given that the actual distribution is normal distribution. So the sampling, oh, here I need to tell you one thing. So if n is large, so how large we'll consider as large? The rule of thumb is if n is greater than equal 30, usually we consider n as large. So if n is greater than equal 30, it's not always true. Sometimes even in n is less than 30, the sampling distribution can be normal distribution. But if n is greater than equal 30, the sampling distribution for mean will become normal distribution, regardless of the distribution of the population. So that's mean regardless of the distribution of the original data. Okay. And this is called the central limit term. So scores on the ACT exam are distributed, which is normal distribution. But if it is given that the data is normally distributed, then for sure the sampling distribution for mean will be always normal distribution. So whatever is the sample size, it doesn't matter. Here it is given the ACT score is normal. So the X bar will be normal. Whether n is less or large, small or large, it doesn't matter. But if this is not given, the original distribution is not given, then you should consider large n to get normal distribution for X bar. Okay, since we have the original distribution is normal distribution, X bar is normal. So what is the probability that a single student scores 21 or higher? Be careful here. This word is important. What is the probability that a single student? So that's mean we are looking for probability for the individual random variable or one single random variable. And in the next one, what is the probability that the mean score? So that's mean we are looking for the probability for mean, not for x. For the first one, the random variable is x. And for this one, the random variable is X bar because we are looking for the probability for mean score of 50 students and the sample size n equals to 50. So, and we have the original mean is mu is equals to this one and variance is equals to 5.9 square. Okay, so I'll give you this one as quiz question. Okay, so now I'll ask you a simple question and let's see whether you can answer this question or not. Okay, so X is normal distribution with mean.
Will this question be referencing the ACT scores that you just showed us?
Sorry?
Will this quiz question be referencing the ACT scores that was just shown in the previous slide?
Yeah. Yeah, the quiz question is this one, the SAT example. Yeah. Scores on the SAT exam are distributed, normally distributed. You have to find the probability that a single student scored 21 or higher. And what is the probability that the mean score of 50 students is 21 higher? So this is your quiz question for today's class. Okay. So here we have X is normal distribution with mean 2.5 and variance is, for example, 20. Yeah, variance is 25. And n is the sample size, n is equals to 100. Okay. So find the distribution of X bar. Okay, so what is the distribution of X bar? Okay, you can just type if it is normal distribution, just type normal distribution with mean, this mean, and variance with this variance. Or if it is normal distribution, then you can just write X normal with mean and variance. Or if it is some other distribution.
I'm going to calculate the mean.
Yeah, mean you have to find, you have to calculate. Yeah, that's the question. Like, if it is normal distribution, then just find the mean and variance. Yeah.
And if it's each other distribution.
Just let me know the mean and variance. You can just type the mean and variance. Yeah. Because I want to see whether you understood this topic or not. Yeah. Yeah, I got one answer, two answers. The PowerPoint is already posted on the Blackboard. You can check Blackboard and it is already there. Yeah. Okay, so I got three answer, 2.5 and 2.5. Okay, so 2.5 and 25. Okay, mean is 2.5, that's correct. But I got like two different variants. Variance would be 5 since it is a square root. The standard deviation is the square root, not the variance. Yeah. Okay. So mean is 2.5, variance is 25. Yeah, mean is 2.5 for both in both case. For x and x bar, they are same. But how about the variance? So I got three different variants, 5, 25, and 2.5. Okay, so if you think that the variance is 25, just type 25. If you think that the variance is 5, just type 5. If you think that the variance is 2.5, just type 2.5, and that will be considered as your attendance. Okay, so if the PowerPoint is different, then yeah, I'll post this PowerPoint on the Blackboard. Yeah, PowerPoint chapter 5. Yeah. Okay, I look at it and I'll post this PowerPoint on the Blackboard. Okay, so I got too many 25. Okay. So can anyone tell me how did you get 25? Why do you think that the mean is, sorry, the variance is 25? Anyone? Yeah, that's the number in the parentheses. Yeah, that's correct. This number, this is sigma square. Yeah, you are right. This is sigma square. But we are looking for the mean of x bar, not x. So this is variance. That's correct. This is sigma square. And this is mu. So what do you know about x bar? The mean of x bar. So the mean of x bar is also mu. We already calculated this one. So what is the variance of x bar? This is sigma square over n. So when you are calculating the variance of x bar, this is not just sigma square. This is sigma square over n. So you have to divide the variance by 100. Yeah, it is 25. Yeah, you're close, but it's not a square root. You will have a square root when you calculate the sigma. So sigma is the very standard deviation. The standard deviation is sigma over square root of n. But when you calculate the variance, this is sigma square over n, not a square root n. So it will be 25 over 100. So this is 0.25. So I didn't get any correct answer, I guess. The variance will be 0.25. I didn't get any correct answer. Anyway, so when you are calculating the variance, this is the sigma square over n. But if you calculate the standard deviation, this is sigma square over a square root of n. That's mean a square root of this number. And mean are, in both cases, mean are same. Yeah. Okay, so we're done with chapter 5. So now we'll start chapter 6, and we'll only cover one section from this chapter. The basic, the point estimation, which is section 6.1. So we'll only cover this section from chapter 6. So the basic principles of point estimation. So first we need to know what is point estimation. So the estimation means we do not know the exact value of the parameter. So could you please give me the name of two parameters? What are the parameters? Anyone? Could you please name two of the parameters? Any parameters? Because before doing the estimation, you should know what is parameter or what are parameters. Yes, the population size. Yeah, you can sometimes it could be parameter. Yeah. Yeah, it's related to population. Parameter is related to population. Population size is not always a parameter, but for some distribution, maybe for gamma distribution, sometimes it might be parameter. Yeah, for some statistics. Yeah, but the parameters are okay. So I got one. Yes, the mean. That's mean the population mean, right? Yeah, the population size. Yeah, is if it is unknown, yeah, it's kind of parameter, but it's not directly a parameter, but it might include in a parameter. Yeah, the population mean is parameter. Sample is not a parameter because the sample size comes from sample, so it's not a parameter. So the population mean mu is a parameter, sigma square is parameter, sigma is a parameter. So these are the parameters, and we can have some other parameters also. We can have alpha, beta for some other distribution. And if you remember the exponential distribution, we had alpha, beta for gamma distribution. And if you remember the exponential distribution, the parameter was lambda, right? So these are the parameters because they are related to population. They are the characteristics of the population. But if and s square is x bar, they are statistics. So these are parameters. And these are statistics. Statistic. Okay. Because they are related to sample and these are related to population. So from where the estimation, the word estimation came from. Okay. We do not know the value of the parameters. That's when we do not know the value of mu, we do not know the value of sigma square, we do not know the value of sigma. So what we can do, we can just collect a sample, and from this sample we can calculate some statistics, and based on these statistics we can make inference about these parameters. For example, we can collect a sample and then we can collect sample mean, and we can make inference about population mean. That's mean based on the value of x bar we can make inference about mu. For example, in our class we have total 53 students, so if we want to know the midterm average of these 53 students, we do not want to collect a score from each students. We can just randomly select 10 students, and from them we can just collect their score, and we can take the average, and based on this average we can tell that the average score of this class is this one. So this is called making inference about parameters based on statistics. So what is point estimation? So we do not know the exact value of mu. We do not know the exact value of sigma square. We do not know the exact value of sigma. So we can collect a sample and we can calculate statistics. So this statistics is related to population mean mu. So this is just a single value. X bar is just a single value. So we are making inference about mu based on a single value, based on a point. That's why we are saying this estimation is a point estimation. So x bar is a point estimate of mu. So we can also make inference about mu based on the median. We can also make inference about mu based on the mode. So they are also point estimation. So for mu, we can have different point estimations. X bar is a point estimate for mu. X tilde median is also a point estimate of mu. And mode is also a point estimate of mu. Similarly, we can make inference about sigma square based on s square or some other statistics. So this statistics is also a single value. And we make inference about this parameter based on this single value. So that's why this statistic is called the point estimate of sigma square. And similarly, based on the value of s, we can make inference about sigma. So s is also a single value. So that's why this is also called a point estimate. So is it clear why we say the point estimation? Because there are two different type of estimation. One is point estimation. The other one is interval estimation. So in the next chapter, we'll talk about interval estimation. Okay, but in this chapter, we'll cover only point estimation. So a point estimate of a parameter theta. So theta is a parameter here. A single number that can be regarded as a sensible value for theta. So that's mean a single value which can be used to make inference about theta is called a point estimate of parameter theta. And this is obtained by selecting a suitable statistics. So based on a statistical value, statistic, you will make inference. And will compute its value, will compute these statistics from given sample data. So from a sample data, we'll calculate the statistics. And based on this statistic, we'll make inference about the parameter theta. And the selected statistic is called the point estimator of theta. So both the estimate and estimator are denoted. Usually we denote it by theta hat. So if theta is parameter, then point estimate is theta hat. Theta hat is this is parameter. And this is the point estimate or point estimator, whatever it is. Similarly, if mu is parameter, then mu hat, this is mu, and this is mu hat. This is point estimate. Okay. So we have one example here. All values given in thousands of dollars. So we have house prices. So 144, 98, 204, 177. So these examples from our first chapter, I think. 155, 316, and 100. So now we have to calculate. So we calculated X bar. This is X tilde, and this is trimmed mean 14.3. That's mean 29% trimmed mean. All of this are point estimate because this is a statistic. This is also a statistic. This is also statistics, and all of them are single value. So this is just a single value. This is just a single value. This is just a single value. You can also calculate the mode, and mode is that's mean the number which here we do not have any mode actually because no number occurs twice or yeah, they just occurred once, so we do not have any mode for this one. Okay, so all of these are point estimate. Now the question is, which point estimates will we will use to estimate the parameter value? And to estimate the parameter value and which estimate you will be using to determine this, actually we have to take several things into our consideration. So how do we know which one to use? You can have several point estimates, but you have to determine which estimate you want to use. So one thing is you have to consider an estimate which is unbiased estimators. So what is unbiased estimators? A point estimate theta hat is said to be unbiased estimator of theta if expected value of the estimate is equal the parameter for all possible values of theta. So for any possible values of theta, if the expected value of the estimate is theta, then that will be called, that statistic or that estimate will be called unbiased estimators. So if theta hat is not unbiased, the difference is called the bias of theta. Difference of expected value of theta hat minus the parameter. If it is not equal 0, then this is called the bias of theta. Then we'll calculate the variance of the estimator. Then based on these two things, usually based on biasness and variance, we will determine which estimator we'll be using to estimate the parameters. And this is called the biased variance trade-off. Okay, so now I'll go back to our calculation of our mean for X bar. If you remember here, okay, you can see here the mean of X was mu. Now if we use X bar, that's mean 1 over n of xi to estimate mu. Now the question is it unbiased? Okay, is it unbiased estimator? Anyone? Is sample mean an unbiased estimator for mu in this case, when xi's are identical and independent? Anyone? Okay. So I got several answers and all answers are no. Okay, so why do you think that this is not an unbiased estimator? Okay, the definition of unbiasedness is, you can get to the new page. So if theta hat is a parameter, and theta hat is estimator, so if expected value of theta hat is equal theta, then this is called unbiased. This is an unbiased estimator. So now we have parameter mu, right? The expected value of X. So this is our parameter. So if we use X bar, so this is our parameter. So X bar is point estimate or point estimator. So what is the expected value of X bar? This is also mu, right? So now the question is it unbiased or biased? So do you want to change your answer? Yeah, it is unbiased. Yeah. Thank you. Because the expected value of X bar is mu. So the expected value of the estimate is the parameter itself. That's mean the difference between the expected value of X bar and mu is 0. So this is an unbiased estimator. Okay, so when it is biased, then you might have different numbers instead of mu. So for example, you can have expected value of maybe x bar is equals to, maybe you can have n times mu or mu plus something. It depends on the statistics. It depends which statistics you are using. So for example, yeah, you are welcome. So for example, if you use x bar plus 3 as estimate. So for example, if you use this estimator for mu, then you can see here expected value of x bar plus 3 is equal expected value of x bar plus this number. So this is mu plus 3. So then the expected value of x bar minus mu is equals to mu plus 3 minus mu, which is 3. So that's mean this is not 0. The difference is not 0. So this is a biased estimator. So this is a biased estimator, x bar plus 3. Or if you consider other estimator instead of x bar, for example, x bar, 2x bar, then it will be 2 mu. So they are biased estimator. This is also an estimator, x bar plus 3, because this is also a statistic, right? Because x bar is a statistic, you are just adding a constant with this. So this is also estimator. Yeah, very good question. Okay, so the when choosing among several different estimators of theta, choose one that is unbiased. Usually we choose the unbiased estimator, but we do not always choose the unbiased, but most of the time we choose unbiased estimator, because the unbiased estimator in most of the time it is the best estimator. So this is why we use S square as the estimator of sigma square hat. So we use this estimator, these statistics, to estimate sigma square. We do not use this one, 1 over n summation of xi minus x bar. Instead of this one, we use this statistic for sigma square, because this is an unbiased estimator. Okay, so if x1, x2, xn is a random sample from a distribution, so that's mean they are random sample, means they are identical and independent, and with a distribution with mean mu, then sample mean is the unbiased estimator of mu. It is always true, and we already showed this, right? We calculated the expected value of x bar, and we found the expected value of x bar is mu when xi's are random samples. So that's mean xi are independent and identical. So when xi's are independent and identical, x bar is always an unbiased estimator of mu. Okay, so if additionally the distribution is continuous and symmetric, okay, so if the distribution is continuous and symmetric, then the sample median and any trimmed mean are also unbiased estimator of mu. So why this is true? This is true because when the data is continuous and symmetric, then the sample mean and sample median are same, and the trimmed mean are also same. So that's why the trimmed mean, the median, and sample mean, all of them are same. So that's why all of them are unbiased estimator of mu. Okay, then we have to look at the variance, and we'll consider the estimator which has minimum variance. Why minimum variance? Our parameter is theta. So we always want to get a value which is very close to theta, right? So we want to estimate this one so that the estimate is very close to theta. So that's mean we want to minimize the variance between our estimator and theta, right? Our parameter. And the resulting theta is called the minimum variance unbiased estimator. So if theta hat is, this is unbiased, and if this one has the minimum variance, then this estimator is called the minimum variance unbiased estimator. And this is called MVUE, minimum variance unbiased estimator. And this is not always the best estimator. Most of the time, the best estimator is UMVUE. This is called unique minimum variance unbiased estimator. Unique means we have just one estimator, and which is minimum variance, and which is also unbiased estimator. This is called UMVUE. So we are not going to discuss this one. So this is, so now we have a theorem here. Let x1, x2 up to xn be a random sample. So that's mean they are independent and identically distributed, and they came from a normal distribution with mean mu and a standard deviation sigma square. So that's mean xi are normal distribution with mean mu and variance sigma square. So in this case, mu hat, which is the estimator of mu, is equals to x bar. That's mean 1 minus summation of xi. This is the MVUE for mu. What is MVUE? This estimator has the minimum variance. So that's mean expected value of mu hat. This is unbiased. So that's mean this is 0. The difference is 0. And the variance between mu hat and mu is the minimum. It has the minimum variance. So that's why this is called MVUE. And when xi is a normal distribution with mean mu and sigma square, then x bar is the MVUE for mu. Okay, now we'll discuss standard error for an estimator. So what is the standard error? So the standard deviation of a random variable is the square root of the variance. We can, since the statistic or the point estimate is also a random variable, because this is a statistic and a statistic is the function of random variable. So this is also a random variable. So we can calculate the mean, we can calculate the standard deviation. The standard deviation of an estimator is called the standard error. Usually, instead of standard deviation, we call it a standard error. So this is the standard deviation. This is the variance of theta hat. So that's mean theta hat is our estimator, and variance of theta hat, variance of the estimator. And if you take the square root, this is the standard deviation of the estimator. So the standard deviation of the estimator is called standard error, or SE. You need this concept for confidence interval. When you will be constructing confidence interval in next chapter, you will be using standard error. Okay, so often standard error depends on unknown parameters. So we must use estimated standard error instead. Okay, so when you will be calculating the standard deviation of your estimator, sometimes it includes a parameter itself. So if you calculate the standard deviation, it will include the parameter itself. So if it has a parameter itself, so that's mean you do not know the value. These values are unknown because we do not know the value of the parameter. In this case, you have to use the estimated standard error. And for sigma, the estimated standard error is, for example, for mu, for random sample, for mu, the mu hat is x bar. And you know that the variance of x bar is sigma square over n. You can see here the variance is sigma square over n. So that's mean it includes the parameter sigma itself, right? So if you want to use this one, you have to use the estimate of sigma, not sigma, because sigma is unknown. So the estimate of sigma is sigma hat, and which is usually the sample variance or sample standard deviation for sigma. Okay, so choice of point estimate can depend on the population distribution. So sometimes it depends on the population distributions. That's mean how your data is distributed. And sometimes the standard error cannot be calculated. So this is the complications. So as a point estimate, you cannot, it depends on the population distribution. And if you do not know the population distribution, then it is very difficult to calculate the point estimate. And sometimes standard error cannot be calculated using standard techniques. So sometimes the standard error is a function of random variable and which is very weird function, and which is you will not be able to calculate that function. So in that case, what we do, we use simulation, and which is called bootstrap. And we are not going to cover these topics in this course. Okay, so this is all about chapter 6. Do you have any question? Okay, so if you do not have any question, I'll give you one problem because we have 18 more minutes. Okay. So for example, x1, x2, and x3, they are normally distributed with mean 3 and variance 16. We have only 3 observations, x1, x2, x3. So now we have x1 is equals to 2, x2 equals to 5, and x3 equals to 3. Okay. So what is the point estimate of mu and sigma square? Okay. So do this example now and try to do this and let me know the results. What do you get for the point estimate for mu and sigma square? Okay, calculate the point estimate of mu and sigma square. And you can also check whether this point estimates for the mu is unbiased or not. So I'm giving you 5 minutes, 7 minutes. If you have any question, if you do not understand how to calculate the point estimate, please let me know. Yeah, I already took attendance today, but if you missed the attendance, then you can just let me know the answer, and that will be considered as your attendance.
Did you take attendance for the earlier question?
Yeah, today attendance, it was not just yes no, it was I gave one problem and the answer was the attendance. So
Okay,
if
that
you
earlier
that
question you
one,
gave.
then you can just simply let me know the answer for this one, and that will be considered for your attendance. Yeah, if you already sent the first attendance, that's fine. Yeah. Yeah, that was the attendance. Yeah. Okay, so that's fine. You can give the answer now. You can give the answer for this question. Okay, so for a sigma square, you cannot calculate actually sigma square, but you can calculate the estimator for sigma square. And the estimator for sigma square is S square. So first calculate the estimator for mu. Okay, so you got 6. So did you get 6 for mu or sigma square? Okay, so you got 6 for mu. Okay. Okay, so many of you got 6 for mu. Okay, let me check whether it is correct or not. Okay, so what is the point estimate for mu? So what is the point estimate for mu in this case? Anyone? Just X bar, yes. I was looking for that answer. Thank you. So the mu hat is X bar. Mu hat is X bar, and X bar is 1 over n, and here n is 3 because we have only 3 numbers. So 1 over 3 summation of 1 to 3 xi. So that's mean 1 over 3 summation of 2 plus 5 plus 3. So this is actually 5 plus 3, 8, 10 over 3. So this is the point estimate for mu. Yeah, mu is 3.333. Yeah, you're right. Thank you. Yeah, X bar is 3.333. Yeah. So this is the point estimate for mu. Yes. So now we have to calculate the, okay, the point is, yeah, it's just average. Yeah. Yeah, it should be 1 over n. That's mean 1/3. And the point estimate for sigma square is a square, and which is 1 over n minus 1 summation of xi minus x bar square. Yeah, your attendance will be counted. It doesn't matter whether you got correct answer or wrong answer. Yeah. Now you do not need to type the correct answer to get attendance. Okay, so now we have 1 over 3 minus 1, and x1 is 2, so it will be 2 minus 3.33 square plus 5 minus 3.33 square plus 3 minus 3.33 square. So this is the point estimate for sigma square. So that's mean the sample variance. So now you can use calculator to simplify this one. Okay, so you got 2.3333 for sigma square. Yeah, I'm not sure whether this is correct answer or not. Yeah, you can check if you can use calculator to simplify this one. If you get 2.33, then yeah, that will be the correct answer. Okay, for actually this is true for random sample, and if it follows normal distribution, then this is always true. The point estimate for mu is always x bar, and okay, so you also got 2.33. Okay, yeah, maybe this is correct answer. Yeah. Okay, 2.33. Oh, so I got one different answer, 3.65. Okay, then I can check which answer is correct. So here we have 2 minus, so that's mean we have 1.33 times 1.33 plus yeah, it should be, the correct answer should be 2.33. Yeah, the correct answer should be 2.33. Yeah, the correct answer. Yeah, many of you got correct answer, 2.33. Yes. Okay, so any question? Okay, so in WebAssembly, you do not need to put any repeating. If you have repeating number, it will ask you to put maybe 3 decimal places or 4 decimal places. Okay, so you got 2.33. Yeah, that's correct. Okay, thank you everyone. See you on Thursday. And if you have any question, you can ask me, okay? Yeah, it will just ask you to round it. Yeah. Okay. You're welcome. Yeah, just one quiz question from lecture today. Yeah, I will ask you to submit the quiz next week, and you will upload your answer on Blackboard. I'll create a folder there, and you will submit your quiz there. And I'll email you the details by this weekend. Yes, it will consist all of the quiz questions. Yeah, I'll provide you the answer once you submit the quiz, okay? Or if you have any specific question, you can ask me. I'll try to answer your question. So which part you didn't understand? So I need help with, yeah, part B, C. Okay. So this is from chapter 5. Last quiz means quiz from last class. Okay, gamma function. Okay, let me check. Gamma function is, I think it's 4.4. Yeah, let